In the 2014 movie Interstellar, filmmakers took great care to make sure that the science behind wormholes in a black hole named Gargantua was as scientifically accurate as possible. Wormholes were depicted correctly as a tunnel with two mouths that are spatially separated from each other and exist in different galaxies. And Gargantua, too, was shown accurately as a region of space where the laws of physics cease to function. The accretion disk was also correct, as well as the fact that the closer one gets to a black hole, the slower time passes relative to a distant observer. But there's one scene where scientists may disagree with the filmmaker's approach, and it has to do with what happens when someone falls into a black hole. In this video, we analyze the science behind falling into a black hole and find out if the dramatic events that take place in the movie are possible or just science fiction. Before we can understand how someone would fall into a black hole, we need to first know what a black hole is. Black holes are one of the most fascinating astronomical phenomena known to mankind. They challenge everything we know about physics, but these enigmatic regions of space were only discovered through Albert Einstein's theory of relativity. Einstein developed two theories of relativity: his special theory of relativity and his general theory of relativity. His special theory explains kinematic time dilation, which means that the faster an object moves, the slower time passes for that object relative to a stationary observer. For example, according to Einstein, if you were traveling near the speed of light, time would pass so slowly for you that decades could go by on Earth while you are only aging a few years. However, Einstein's special theory only applies to objects that move at constant speeds in a straight line, meaning it doesn't apply to objects under the influence of gravity. For example, it does not explain what happened to time on Earth. That's because the effects of gravity had not been considered. So Einstein went further and developed his general theory of relativity, which not only explains kinematic time dilation, but also gravitational time dilation. The general theory of relativity states that the stronger the gravitational field, the slower the time pass. This means that time would pass more slowly on Earth than it does in space. And this is exactly what happens if you had two identical clocks, one on Earth and the other in space far away from any gravitational field. The clock on Earth would tick more slowly than the one in space. So how did Einstein figure all this out? Well, he had some brilliant insights. One of them was how to visualize gravity. According to Newton, the force of gravity comes from an interaction between two objects with mass. The more massive an object, the stronger its gravitational pull. However, this view of gravity did not sit well with Einstein. His idea that the speed of light is constant. After thinking deeply about the issue, Einstein came up with an idea that revolutionized our understanding of gravity. He imagined that massive objects warp the space around them in such a way that other objects move towards them. In other words, he visualized gravity as a bending or curvature of the space-time fabric caused by massive objects. This means that massive objects do not pull on other objects. Rather, the presence of a massive object distorts the space-time around it, causing other objects to move towards it. This distortion of space-time is what we experienced as gravity. Now, let's see how this relates to black holes. A black hole is an object with such immense mass and density that its gravitational force is strong enough to trap even light. Light travels at the fastest possible speed in the universe. If something can trap light, then it must have an incredibly strong gravitational force. Black holes are formed when massive stars run out of nuclear fuel and can no longer sustain the outward pressure needed to balance the inward pull of gravity. When this happens, the star collapses under its own gravity and forms a black hole. To be more precise, this occurs when a star's mass exceeds a critical value known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Stars more massive than this collapse directly into black holes. However, those with masses less than this limit do not. Instead, they form white dwarfs If a star's mass is exactly at the Chandrasekhar limit when it collapses, it forms a neutron star. These limits define the maximum mass for white dwarfs and neutron stars. There are 4 types of black holes. Stellar black holes are those that form from the collapse of massive stars. Primordial black holes are hypothetical black holes that are thought to have formed in the early universe. Supermassive black holes are giant black holes found at the center of most galaxies, including our Milky Way. Finally, intermediate black holes are hypothetical black holes that are intermediate in size between stellar and supermassive black holes. It's important to note that black holes are not cosmic vacuum cleaners. Despite their powerful gravitational pull, they do not actively suck in matter. Rather, they exert a powerful gravitational force on nearby objects, causing them to orbit around them. Planets orbit the sun in much the same way that objects orbit a black hole. However, if an object gets too close to a black hole, the gravitational pull becomes extremely strong and tears the object apart in a process known as... This occurs because the gravitational force is stronger near the black hole. As an object approaches the event horizon, the gravitational force on one side of the object becomes much stronger than on the other side. This difference in gravitational force stretches the object like spaghetti. This phenomenon is demonstrated in the movie Interstellar, where the astronaut Brand falls into a black hole. As he approaches the event horizon, the gravitational forces stretch him into a thin line. However, this process would actually happen much faster in real life due to the intense gravity near a black hole. Another interesting feature of black holes is the glowing ring of light around them. This ring is called an accretion disk, and it is formed by gas and debris that is heated to millions of degrees by friction as it moves around the black hole at incredible speeds. The brighter the light around a black hole, the more active it is. The boundary of a black hole is known as the event horizon. It's the point of no return beyond which nothing, not even light, can escape. Once something crosses the event horizon, it can never come back out, and it is impossible for anyone to observe what happens inside a black hole. This is why the interior of a black hole is often referred to as the cosmic abyss. To summarize, black holes are fascinating astronomical phenomena that have challenged our understanding of physics. They are formed when massive stars collapse and exert a powerful gravitational force on nearby objects. While the exact mechanism by which an object falls into a black hole is complex and involves intense gravitational forces and the stretching of the dramatic depiction of this process in Interstellar is broadly consistent with scientific understanding. The idea of a black hole tearing an object apart like spaghetti is a dramatic and memorable way to convey the immense power of these cosmic objects. And the glowing ring of light that surrounds a black hole adds a visually striking element to our understanding of these mysterious phenomena. But what do you think? Is there anything we missed? Let us know in the comments below. And don't forget to subscribe for more videos about space, technology, and the latest scientific discoveries. Thanks for watching, and we'll see you next time.